So now we are going to talk about something which is slightly more advanced than all of that. Cool guys, so now we are going to talk about the final section of today's lecture, which is basically something called stacking. But before we start into stacking, let's get an intuition of what is stacking. So stacking was something we have kind of slightly touched upon all of this while we did not talk explicitly about it. So we have the same one, this entire training data set, right? This is your training data. And what you have done is train multiple models on them, right? So M1, M2, M3, M4. Now your soft voting concept was, for a new data point, for a new test data point, you would have probabilities P1, P2, P3 and P4, right? Say of class 1 from each of them, and you combine them, right? So you average them. And that's your final prediction probability, right? So that was called soft voting. Now in case of hard voting, we thresholded them, this P1, P2 values to 1 or 0 values, and then kind of took what is the majority of either it's 1 or 0, and then that's your decision. That was hard voting. And what did we do with specialist models is basically split this data set into multiple parts, right? Multiple parts, and then we again train models, each of them on M1, M2, M3, right? So this is a model M1, M2, M3. And what did we do again? So after we have trained on each of them, we have probabilities P1, say P1 dash, P1 dash, P1, P dash 2 and P dash 3, right? So you have this, and again what you did was you took an average of all of this, right? But then obviously, as we have already discussed, while what are the different techniques to aggregate, we had talked about weighted average, we had talked about some other techniques where the weights were decided based on accuracy of each of these models. So the same concept still exists here, right? Why are we doing a simple average? Why shouldn't we talk about something which is more exotic? So what is the exotic concept? Exotic concept is this, that instead of taking a simple average, we should take a weighted average, right? So W1 P1 plus W2 P2 or W3 P3 plus W3 P4. So this is a weighted average, right? So this was an exotic concept. We had discussed also how to come up with these weights, right? So now that we are talking about something even more exotic than that, which is basically instead of you deciding these weights as per based on accuracy or AUC or error or anything, why not let another machine learning algorithm learn all of these weights? And even more importantly, why only combine them in a linear way like this? Why not take something which is a non-linear model, right? So now let's take a real example to understand what is exactly ensembling, right? So let's say you have multiple models M1, M2, M3 and M4, right? So this M1, M2, M3 could be trained on the same data, like what we did for soft voting. It could be trained on subsamples of the data, like what we did in bagging or pasting. You could train on multiple stratum of data that we had discussed. So there could be multiple ways you could train each of this model. But let's now say for a given test data point, it gives you a probability P1, it gives you a probability P2, it gives you a probability P3, and it gives you a probability P4, right? So what we did was for soft voting as well as for bootstrapping pasting, we did the most naive thing possible, which is basically take an average of all of this, right? But in real life, and obviously probably for more sophisticated Kaggle winning challenges or in research problems, you really don't want to just take a right up average like that, right? So what do you want to do? You want to probably combine these probabilities, right? And as I already explained in the previous slide, that how you combine them is basically using a machine learning. So what happens now? So now you train another machine learning algorithm, which is called a meta classifier, whose input are the probabilities from your models, 5 models or 4 models, whatever you have, and it still outputs the same Y target, right, that you had already had used in the earlier case. And it's trained on basically your input is now, instead of the independent features that were used for each of them, you are now training on your independent features are now the probabilities from the first 4 models. And your dependent feature is still the Y target, right? Because you are trying to tell this meta classifier how you combine the probabilities to come to the correct output. So the correct output is still the target values and your input are now the probabilities, right? So now let's try and understand that example through a more, let's understand how you probably would implement this in real life, right? So you would have ideally start off with say 1000 data points. Now out of those 1000 data points, you are going to split this, say 100 of them for test. These are tests. We will only understand how prediction works on this test data set. Now for fitting, you have 900 data points, right? So these are your 1000 data points. You have split into 900 and 100. And now you want to split them further into say 600 and 300. Right, so your original data basically consisted of x1, x2 and say x3, and you had a y target, which is your whether the person was given a loan or not. It's a 0-1 kind of a variable, right? And your x1, x2, 3 were this could be income, this was co-applicant income, this was age and features like this, right? So you had, this is how your original data looked like. You had 3 independent features and you had the one dependent target which you had to evaluate, right? So this is what we are very familiar with this kind of data set, right? So what do you do, how you implement stacking is this. So first what you do is train individually each of the models M1, M2 on this data point, right? 600 cross 3, and your target, this is your x and this is your y is 600 comma 1, right? So you train all your models on this, right? So M2 to M3, let's say, right? So M5, let's say you have 5 models you have trained on them. So M2 to M5 you train on 600 cross 3 and 6. This is your y and this is your x. Now once you train and cross validate them and you kind of have the best model, so what you now do is take this 5 models, prediction on 300 data points. So now what you do is make this models predict the probabilities for this 300 points, right? So for each of these 300 points you would have the predictions like P1, P2, P3, P5, right? And you would have the corresponding 3 for each of those 300 data points. So you would have 300 rows and 5 columns, right? So 300 comma 5, this is your x now, and now you would be training that across your target, which is a 300 comma 1, right? So the corresponding y target for each of these 300 data points, right? So that is what you're going to use. So this is your training data for meta classifier. Now again your M1, M2 could be decision trees, logistic regressions. Same for meta classifier, it could be decision tree, it could be logistic regression, it could be an ensemble in itself, it could be whatever you may want, anything that basically classifies, right? So that's what you need here. So it would be trained on 300 comma 5 and 300 comma 1, right? Once you do that, so now for how does the final prediction on 100 looks like? So for this 100 data points, first you would take their predictions from this 5 models, right? So you would have one model give you 100 comma 1, the second model would give you 100 probabilities, right? So these are 5 sets, 5 models, and now you would combine them into a data point which is 100 cross 5, concatenate them into 1, and then you would finally take, so these are your probabilities, right? So your probabilities. So now you take the 5 model probabilities, combine them into one data set and use this meta classifier which you have trained using this 300 data points to predict the final probability for those 100 data points. So this is the overall implementation structure. I'm sure once you do this in your class or once you do that at your leisure time, kind of go through this once over again, it would be much easier to understand. So the flow, again I'm repeating it for you. So the first you take 1000 data points, then you split into 900 and then you split into 100, and this 900 you again further split into 600 and 300. First you train your 5 models here. It could be 5, it could be 10, it could be any arbitrary number that you may want to go ahead with. So take all of these 5 data points, train them on this 600 data points, right? So for each of the 5 models, the training data is same, 600 cross 3 and 600 cross 1. This is your x, this is your y. So this is what you train all of them on. Now for this 300 data points, what you do is you first take all of these 5 models prediction on all of this 300 data points, right? So first model would give you 300 probabilities, second model would give you 300 probabilities, so on and so forth till your 5 models. Now you put all of those 5 probabilities together like this, and these are your 300 data points. So now you train your meta classifier on this, right? So your X is now this independent probabilities, right? Independent probabilities are 300 data points. This is your, what is your meta classifier looks like. Your meta classifier again could be anything which is a decision tree, logistic regression, any classifier, and that's it. That's your training process kind of completes. Now for testing purposes, what you do is for this 100 data points, first take the probabilities from each of those 5 models and then combine those probabilities in one place and take your meta classifier and train it on that, right? Predict on that. So you have your meta classifier already fitted on this data points. So now you just use that meta classifier to use this 100 probabilities, set of 5 probabilities from each of those models, 100,5 data set, and use that for your meta classifier to predict. That's about it. That's what is stacking all about is. So so one question which kind of still remains unanswered is this: why did we take 900 and split it into groups of 600, 300? Why did not we kind of train our all models on 900 data points and also train the meta classifier on the probabilities of those 900 data points, right? So we'll be talking about that in a while. So probably would be a good moment for you to kind of think about why is there a splitting between 600 300, right? So I've already explained you the stacking concept. So this is the diagrammatic representation. So you have a training data that you have all your models, classifier models C1 to CM trained on the same data. Now on a new data, and this is the part which we kind of overstressing here. Why do we require new data? So we kind of come off to that. But on a new data, you're going to take the probabilities and then you're going to train a meta classifier which takes as input this probabilities, right? So on a new data, you're going to take the probabilities P1, P2, PM. And those P1, P2, PM are now your input to your meta classifier, which finally gives you a final prediction PF. So obviously I've explained to you how this meta class, how this stacking works. I've explained to you, and there's something which we kind of so this is the point where we kind of want to talk about why do we split this decision. Why do we split the training data 900 data points into 600 and 300, which is this, because if we had taken all the 900 data points, right, if we had instead of doing splitting, we had taken say this 600, right, and instead of training on 300, we take the probabilities of all of the models on this 600 data set, then we would get super awesome probabilities, right, because the models have already seen all of the 600 data points, right. It has seen all of the 600 data points and it would give you very awesome probabilities. And what your meta classifier would learn to do if you are training on those 600 probabilities are basically how you combine the super awesome probabilities. So each of those models gives you super awesome probabilities because they have seen those data set already. This is a training data set, so the models have been basically fitted such that they give the best result on the training data, right? So if they have been done that, so they will give super awesome probabilities for all of those 600 points. And now if you train a meta classifier using those 600 probabilities, your meta classifier would learn to combine when you have super awesome probabilities, how to combine them. Whereas in real life cases, you need the meta classifier to learn if on a test data set, your probabilities won't be super awesome, right? On this data set, you still need your meta classifier to learn to combine this not so awesome probabilities, right? So that's why we are using a new data set here, such that you don't have super awesome probabilities. The probabilities exactly look like how it would look otherwise as well. And your meta classifier kind of learns to combine how to combine. So meta classifier also learns how to combine such not so super awesome probabilities, right? So that's why you take your probabilities on a new data set, right? Because if you take on the 600, you have super awesome probabilities and your classifier kind of learns how to combine them. In real life case, when it would get not so super awesome probabilities, it would fail, right? So that's why you train this 600 data points and then you take the prediction on a separate new data set, and then you train a meta classifier which learns to combine this super not so awesome probabilities, right? So these are not so awesome. These are very much like real probabilities that you would get here. The probabilities that you would get from the 5 models on this and this are very similar. So if you train a meta classifier to combine this kind of probabilities, the not so good probabilities, then you would have a meta classifier which would also probably work very well in this case, right? So that is the concept. So we have talked about this. So now I have already explained to you how stacking works with a discrete example. So now stacking is sadly and probably fortunately also not implemented in Scikit. It's implemented in a new library which is called MLXtend. Now the thing to note here is stacking is just what I've told you is just basically one layer of mods. You have one layer of models and then you have another layer which just takes in probabilities from that and kind of finally gives the answer. Now stacking in real life could be multiple levels, it could be multiple different ways. You could have features from one particular model going into the second level of stacking. So stacking is frankly again something that is not to be used directly off the shelf. It's something you are supposed to put your ideas into how you want to do stacking. Do you want to train your multiple models on different types of data? Do you want to give a weightage initially or some cost function while you're training your second meta classifier? So all of these are concepts that kind of goes behind training a stacking algorithm. It's not like you just directly take a off the shelf implementation and directly do it. So please understand the concept, try and build it. And in fact I would encourage you, while you're doing this classes physically offline, please try and implement everything by your hand using Scikit. Don't try and use a library off the shelf like MLXtend. That would probably hamper your learning. Also, when you're trying to do your own creative things, it would help if you learn how to do things by your own hand. So this is how you do it in MLXtend. In MLXtend, you just kind of import the Scikit models for decision tree and logistic regression, and then you just make a list. So this is the list here, right? So the list is of models. It contains logistic regression and decision tree. And then what you do is just take a stacking classifier. So stacking classifier was something that you have seen here is imported from MLXtend, right? So you see here MLXtend has imported stacking classifier. So now what you're going to do is just use the stacking classifier on the same data set and get your final output, which is your accuracy, right? So that's about it. That's about what we had to learn in ensembling. So again, kind of going through the concepts. So first we learned why do we do ensembling. So the concept is simple, right? If you have one model which you know that is not really good, right? You know that each of your models cannot be perfect, right? So you know that it's much better to probably, instead of trusting one model, why not trust more models, right? So this is the concept where it is called ensembling, where you combine multiple weak learners. Weak learners are ones which are performing slightly better than random models. So you combine them into one particular model which is a strong learner. So multiple weak learners, combine them, you have got something which is extremely strong. So that is the concept of ensembling. Now in ensembling we have talked about couple of methods to do that, 3 basically. First was naive aggregation, and naive aggregation was nothing but you train multiple models on the same data set, right? On the same data set, so if there are 1,000 data points in a data set, you train your 5 models on all 1,000 points. And then you somehow combine them. Your combination techniques could be 2, soft voting or hard voting. Soft voting is where you directly take the probabilities and average them. Hard voting was where you take the class predictions and then take a majority of those class predictions, right? So that was soft voting and hard voting. Now came the idea of specialists, right? So where we thought that, you know what, why train every model on the same data set? If there's 1,000 data points, let's split them into 10 parts of 100 points each, and now train 10 models for each of those 100 data points and then combine them, right? So that was the idea of learning specialists, and there we talked about specifically two of them, which is called bagging and pasting. So what was bagging again? Bagging was bootstrap aggregation, where you took data sets where those 100 data points were selected with replacement. Pasting was those case where out of those 1,000 data points, the 100 data points in each sample was selected without replacement, right? So that's about it. That's the difference between bootstrap and pasting, and we saw that on an average bootstrap might tend to do better, but again that's an indicator statement, don't try and go ahead with that. And then we finally talked about stacking. Stacking was a concept where we had multiple models trained on it, but instead of doing naive aggregation, soft voting kind of things, right, where you're just directly averaging the probabilities, we said, you know what, train another machine learning algorithm which kind of learns how to combine the probabilities, and that's exactly what stacking is. Now, given all that we have discussed, before concluding, there's one thing which I would obviously say, and I would kind of reiterate that I've been saying that throughout the session, is that while discussing ways of aggregation, I talked about multiple methods, and trust me, and I would really encourage all of you to think more methods, because trust me, if you go out in the real world, there are a lot more methods than the ones we have discussed here, right? So the ways you can aggregate the probabilities, right? The most sophisticated one we have discussed somewhat is called stacking, where you train another machine learning to combine the probabilities. It could be something else. You could take weighted average, you could take cluster means, You could do a lot of different things in that case. So that's one technique. That's one thing I would like you to think about. And also how you train your models, right? In case of specialists, at least when you're splitting the data into multiple parts, right? How do you split those data? What are the possible options? Do you always randomly subsample? That is obviously randomly subsampling are basically the types which are bagging and pasting. But apart from randomly subsampling, we have talked about stratified sampling, where you take data from multiple strata and build models for each of them. We have talked about all of this. Please go and kind of put some time also into figuring out, thinking about new ideas, how you can split your data set into multiple parts for your different ensemble models. And that's about it. So please keep your eyes open. Please try and think as much as possible. Be creative. And trust me, this is what kind of makes you a very good data scientist, a distinguished data scientist from the rest of you guys, right? So rest of everyone is kind of going through the same lecture, right? What you are doing, what you're thinking, and how you're perceiving the data, how you're making intuitions out of it is what defines you. So on that note, I will end the lecture here. I'll see you for the next lecture soon.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.